The thing we're going to do in lecture today is we're going to introduce the concept of electric field. This is actually the most important concept we'll encounter in the entire course, and we're going to talk about it every single day of the semester. So we're going to start now. A little background. You know from your chemistry courses that matter is composed of atoms, and atoms themselves are composed of really tiny charged particles. Charge meaning they have an electrical charge, which we call either positive or negative. And you know about some of these particles. You know about a proton. It has a mass of about 1.7 times 10 to the minus 28th kilograms. It's a really 27. Sorry, I know that. 27 kilograms. It's a really tiny particle, and it has an electric charge of sort of an odd value, 1.6 times 10 to the minus 19th coulombs. The unit of charge in SI units is 1 coulomb, and you can see that it's probably kind of a lot of charge if the charge on one proton is 10 to the minus 19th coulombs, but those are the units we're stuck with. And these are the units we'll be working with. And it has a positive sign. You know about electrons also. An electron is much less massive than a proton. It has a mass of about 9 times 10 to the minus 31 kilograms. And its charge is minus 1.6 times 10 to the minus 19 coulombs. So it has a negative charge exactly opposite to the positive charge on a proton. As a matter of fact, this seems to be the smallest amount of charge we can ever observe in a particle that we can observe. We can see 1.6 plus 1.6 times 10 to the minus 19th coulombs, or minus 1.6 times 10 to the minus 19th coulombs. We never see half of that. We can certainly see twice that if we put two protons together. We have reason to believe that the subatomic particles, the quarks that make up protons, have charges of plus or minus 2/3 of that, but we can never get them alone. They don't like to occur alone, and they always occur in combinations that give us one of these charges or zero. This number comes up so often that we have defined a constant to represent it, and this constant is called plus little e. Let's see if I can find a marker that actually writes plus e. Now, just as if we didn't have enough uses for that letter already, this is not the natural log base, and this is not the thing you sometimes write to denote an exponent. This is a positive number with a value 1.6 times 10 to the minus 19th coulombs, and so the charge on an electron is then minus e. And there's a bunch of other charged particles that you might know about that we may encounter. There's an antiproton. We sometimes write it as a p minus. It has the same mass as the proton, but it has a negative charge, a charge of minus e. There's also the positron, which is an anti-electron. And its mass is the same as the mass of the electron, but it has a charge of plus e. Now, these guys don't stay around very long because they tend to react very violently These are antimatter particles, and they tend to react rather violently with these ordinary matter particles when they run into them. And so in our neck of the universe, where there's lots of protons and electrons, these guys don't last very long because an antiproton might run into a proton and annihilate, producing lots of energy in the form of photons and maybe some other particles. And there are some other things like muons. These are kind of like heavy electrons. They have a mass that's a little bit larger than the electron. There's a mu plus. It's something like about 1.9 times 10 to the minus 28 kilograms, and there's also a mu minus. And we do detect these things on Earth because they get created, and they're what people used to call cosmic rays, and we get showers of them when charged particles hit the top of our atmosphere, and we'll run into them later in the course. And there are also pions and things like that. So there's a bunch of charged particles, and the thing about charged particles that's important is they all interact electrically with each other.